Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please go ahead and pause the video right now, subscribe, and continue. We've been talking about segmenting BraTS2020 dataset for the last 3 videos, and let's finish that discussion today by actually training and predicting. Okay, and what have we done in the last 3 videos? In the first one, we laid out our plan. In the second one, we got the data ready. And in the one after that, we defined a custom generator and we got our data into the respective folders, training and validation, everything is ready. Now, if you haven't watched those videos, I definitely recommend you to do that first because you'll have the data ready to be used, especially if you want to follow the process that I'm going to show later on in this video. Now, just a quick reminder, in case you have had some gap between these videos, just a quick reminder, BraTS dataset, go ahead and download that first. It's 40 gigabytes, unzip it, and then the quick information about dataset. You have multiple channels. This is a multi-channel or a multi-band, if you want to call that, dataset, which means from the same field of view, you have four different views. One is our 4 different volumes. One native, which is labeled as T1. The other one contrast weighted, T1CE. The next one T2 weighted, T2, and then the fluid attenuated. This is acronym FLAIR right here. So 4 different volumes, and then we looked at the images and decided that the T1 is probably not that useful, but T1CE, FLAIR, and the T2 apparently looks interesting, looks useful for training our model. So we combined these 3 volumes into a single mega volume, okay, with 3 channels. And then we took our mask and we also created a NumPy volume out of this. And what do we have inside the mask? We have basically 4 labels, 0, 1, 2, and 4. And 0 is all the unlabeled volume. And 1, 2, and 4, there's something meaningful. 3 was missing, so we reassigned our 4 to 3 later on. And also, we tried to eliminate as much of unlabeled volume as possible. That's where we were. And now let's go ahead and jump into the code to see how we can proceed from this point. Okay. Okay, and I am back to the Spider IDE just to show you. We started off with getting the data ready. Again, I don't want to bore you guys who already watched these videos by going through everything. At a high level, we got the data ready using this code, which I have already shared. And then we defined a custom data generator where we defined a way to load images. In our case, we converted our original images, chopped them into smaller pieces, and converted them into a NumPy array because that's the easiest way to handle our data. So we defined a function to load the images, and then we defined our image loader. Instead of using Keras data augmentation process, which requires our images to be either in TIFF file or JPEG, and if it is in a NumPy format, it doesn't understand that. If you guys know tricks to work with that, please leave that in the comments, but this should work equally well. Here I am basically defining a way to load our volumes in batches, and the batch size is something that we provide as an input. And then we tested the generator just by loading a batch size of 2, and on the right hand side you can see that it's actually working very well. Everything is lined up. So far this is where we are. So let's clean the slate. I left the screen up so you guys can see it. In fact, I didn't shut down my computer in a couple of days with this screen there. So I can start with that. Let me clear everything. And the next part. So what do we want to do now? First thing, you need to define your 3D unit. You can get that from Segmentation Models library or any other library that offers 3D unit, or you can write your own from scratch. The way I decided to proceed was to minimize any complexity. So I just took my 2D unit and converted that to 3D. This is the same 2D unit that I have used for many times in the past. Okay, and this is the same unit that I have used for sandstone segmentation, I believe, in the past. Okay, so first I defined a function, Jacquard coefficient, but for now we can ignore that. The meat of this is right here. This is a multi-unit model with a number of classes 4 and image height 256, width 256, number of channels 1, right? So this is 256 by 256, no third dimension. And all my convolution operations are 2D, conv 2D, max pooling 2D, conv 2D, conv 2D, max pooling 2D. And The kernel size is 3 by 3, 2 by 2. I took exactly the same, except, you see, everything would be exactly the same, except I changed my conv2D to conv3D. Okay, if I go back here, I changed my conv2D to conv3D. Let's go down here so you can see it right there. When I switch back and forth, all you will notice is my conv2D and max pooling 2D, I converted them to 3D, and I changed these to 3 by 3 by 3 or 2 by 2 by 2 kernels. Other than that, I don't think you need to do much. Obviously, print out and see, the model and see if everything makes sense. Towards the bottom, when I get down here, this is 1 by 1 by 1 final operation. And then what the activation we're going to use is softmax, because we're dealing with multi-channel. Semantic segmentation. If you're only working with binary, then that would be sigmoid. All of this pretty much standard. I think you know that. So let's go ahead and test this out. In fact, down here I'm testing it by calling my simple unit model. Right, this is what I defined right there, and for a size of 128 by 128 by 128 by 3. Remember, this is the data set that we saved right here. We started off with a data set that looks like this, and we combined FLAIR, T1CE, T2, and then chopped that off into or cropped it into a smaller size of 128 by 128 by 128. Because we have 3 channels, you have 3, and then saved all of that into a NumPy array. Let me get back into a NumPy array, into multiple NumPy arrays, right? And then divided that into training and validation. So if I go into train, you have images and masks, and my images are all NumPys right there. Okay, and each of this, like I said, is 128 by 128 by 120. By 3. Did I do something there? Yeah, by 3, and the 4 is basically our number of classes that we have. Okay, so let's run this entire thing. There you go. I just want to make sure you see how the model looks like when you print it out. Okay, so when you go all the way to the top, too much. So it doesn't show you what the actual full input is. I mean, it's showing you the next level, 128, 128, 12, 128, 128, all of these. And then when you go down all the way, you have 5.6 million parameters that you need to train. So I like to see what the input, is, and what the output shape is. We know what it should be, right? My output is supposed to be the number of classes, my original image with the number of classes right here. My input is supposed to be whatever I define here, right? Image height, width, depth, and number of channels. But once I build the model, I like to check things out. So go ahead and print out the model input shape. So that's perfect. When you import external libraries, I did this. I tried to find something on GitHub, and I found something that said 3D unit. But when I printed this out, it just gave me 128, 128 by 3. That's it. No Z dimension. So anyway, I thought it's easier for me to just do my own thing, so I have full control. Yeah. So this is the input, and the output should be exactly that, except 4 channels, right? 4 channels because we have 4 classes, and then we'll do argmax to convert that into our classification at a given pixel. So this is my 3D unit. So we have our 3D unit ready. So finally, let's close all of these and focus only on our training part now. So let's get ready. Let's clear everything and get started. Okay, so far our images are expected to be, I guess in our case, we saved 128, right? So I should say, or 128 by 128 by 128 by 3. Again, I was experimenting with various of these, and I took some notes right there. So if it says 256, 256, it can be 64 for you if all of that doesn't fit into your memory, right? So work with whatever size you think you can handle. Also try Google Colab to see if you can work with 128 by 128. Yeah, right there. Okay, so Sorry about bookkeeping in the middle right there, but these are important things. Okay, now let's come down and run these lines. And in fact, this one we are not even going to use. So let's go ahead and comment that. OS is to walk through the files. NumPy, of course, you know what that is. And custom data generator, import image loader. I closed it, but this is what we created the last time, custom data gen, right? We just looked at this. So from here, we are importing image loader. So we can load these in batches. Import keras. Well, it could be tensorflow.keras, but I'll leave that to you. Matplotlib, pyplot, glob, and random, right? I mean, again, to walk through directories and everything. So again, nothing new over there. And the next step, let's define our directories where our images and masks are stored. So my images are in train/images, masks are in train/masks. Again, you know that. Training data, 128, train, and images and masks. Okay, now let's extract the file names. We have done this before, but again, for those of you who like to see things being repeated. Okay, so these are basically my image list, image names, and mask names. Now, I just want to randomly open some images and have a quick look. We have done this in the last video, so I'll go through this a bit fast. So now, why am I doing this? Because I'm crazy, because I really want to make sure things make sense before I spend how much ever time trying to segment this data set. Again, one last time, right? So there you go. This matches very well with this image. As you can see, these images, so that makes absolute sense to me. Let's go ahead and randomly load another slice. This region matches with this and that, so I'm good. Okay, so I know my images and masks are matching up, and I do have 3 different channels that are coming from my input NumPy array, which is where this is where we stored our images and masks. So far so good. Now, I added this optional step in case you would like to find the distribution of each class, meaning if your unit, if you're using weighted, let's say a unit or weighted dice loss, anytime you want to know the weights, because these weights are all not balanced, these classes are not balanced, right? You want to know how much of class 0 you have, how much of class 1, class 2, and class 3. So you can balance things out. If you want to do that, again, this is why this is an optional step. You can follow this part of the code. All we are trying to do is basically look at how many labels of each kind you have, and then dividing each label by the total, so you get some sort of a weights right here. Okay, so I'm going to skip this. When I did that, I got labels of the weights of these, but I'm gonna skip that for now. Okay, I'm not going to use weights as part of my dice loss or any of these operations, but I left it there in case you want to use it. Okay, moving down. Now let's define the image generator for training and validation, right? So we need to supply the images, and how do we do that? First, define image directory, mask directory. How do we, again, let's go back here. Okay. So this is the function we are going to use, image loader. What does it need? Image directory, image list of images, right? Mask directory, list of masks, and then batch size. That's exactly what we are trying to provide down here. So image directory, mask directory, validation image directory, validation mask directory, and then image list, mask list, validation image list, mask list. That's it. Again, nothing new here. Just go ahead and run this so you have those. Now let's do batch size of 2. Why 2? 2 sounds like such a small batch size. Yes, it is small batch size, but think of the size of our volume. These are 128 by 128 by 128, 3 such volumes all fused together into this data set. And now we are loading 2 of those at a time to train. And that's tremendous amount of data. Okay, unless you have very high resources, you cannot get much higher batch sizes. But this is enough data, I think. It would be nice if I have better resources, but I don't, unfortunately. So I'm going to work with batch size 2. The other thing I could have done is, instead of 128, I could have chopped these into 64, 64, 64, 64 volumes, and then worked with higher batch size, but I don't see much of a difference. And in fact, I prefer not to do that, because you would lose context with the rest of the regions, right? I mean, it's nice to have it's nice to have the context provided within the field that you're defining here. I hope that makes sense. Okay, so my batch size is 2, and now I'm going to define a train data generator again, which is basically my image loader with my training directories and masks directories. Yeah, same thing with validation. So let's go ahead and run these lines. So we define our generator again, which means when I run this line, which is run the image data gen, and then next it should give me 2 images at a time, 2 images and 2 masks. Let me go back. We are yielding X and Y. X is the image, Y is the mask. Okay, that's why we are going to get 2 things. The first one is image, second one is mask. Okay, let's run this line. And where is my image? Right there, you see my image is 2 images, each 128, 128, 128 by 3. My mask is 2, 128, 128, 128, 4. Okay, so far so good. Let's go ahead and plot this one more time. This time we are actually checking the generator itself. Again, why am I doing that? Because I'm crazy. I don't trust. I have trust issues here. That's why I'm doing this. I just want to make sure I am seeing what goes into the model.fit. Yeah, this is going in there and everything lines up pretty good. Yeah, I don't like these little things. I don't think anyone annotated these, but anyway, let's go ahead and run this one more time. No annotations here. Annotation here matches very well. Sanity check done. Okay, now let's come down to defining the loss metrics and optimizer. This is where you need to experiment with a few different ones. I did some experimentation with actually adding weights to each class and then defining a dice loss where it takes in the weights. Not much of a difference, in fact. I should say giving them equal weights as part of the dice loss, not much difference by changing this to the weights that we calculate up here. Yeah. But again, I'll leave that. This is what you need to experiment yourself so you gain an understanding of the implications of doing something. Okay, so for now, let's assign the weights. In fact, you don't even need to give any class weight right there, and you can leave that as blank if you want. Yeah, because if you don't give anything, that's almost like, okay, equal weight. Okay, but let's leave that. Okay, so our weights are equal. We have 4 classes, so 0.25, 0.25. And from segmentation models 3D, I'm importing the library segmentation models. Why? Because I plan on using the focal loss and total loss as defined in that library. If you want to use other loss like cross entropy, categorical cross entropy, or you have your own focal loss, that's also fine. I'm just showing you the way I followed. So my dice loss is from segmentation models, get this dice loss with a class weight of that. Yeah, so let's do that. And focal loss is great. By the way, I found out, especially for this data set, if you only use dice loss, that does a pretty good job. If you only use focal loss, it doesn't do as good a job as dice loss only, but then the best combination was mixing dice loss with focal loss, right? I'm adding dice and focal loss, and this actually worked very well. That's what I'm going to use. And in fact, not just on this data set, on most data sets, that turns out to be a pretty decent approach. So I'm going to do that. And for metrics, let's go ahead and track both accuracy and IOU score. Yeah, both of these. So let's go ahead and metrics. And learning rate, we are going to use ADAM optimizer. So let's provide our initial learning rate as 10 to the minus 4 right there. And my optimizer is ADAM. All of this should be pretty straightforward to you. And steps per epoch is how many training images do we have divided by the batch size. That's my steps per epoch. And my validation steps per epoch, how many validation images you have divided by the batch size. Again, nothing unique with this data set here. Okay, and what am I doing here? Yeah, from simple 3D unit, import simple 3D unit model. What is that? Well, we just defined our 3D unit right here, right? So all I'm doing is, hey, from this file, get my simple 3D unit, simple unit model, and I'm going to provide these as parameters right there: image height, image width, image depth, and so on. Okay, number of channels. So let's run these lines. Okay, and now we need to compile the model, compile using optimizer, loss, and metrics. And we already provided the metrics and loss up there. So all I'm doing is just compiling the model using that. And now let's go ahead and print out the model summary. There you go. And again, we just looked at this, so let's go through this pretty fast. 3 128s and 3 for input, good. And for output, it's exactly the same except for 4 channels. There you go. And now you're all set to go ahead and train the model, which I have done. It takes some time, so I'm not going to do it right now. And in fact, let me go back and show you. Let me see if I saved the training curves, so we can have a quick look at how the results look like. Okay, just give me a second. Well, it looks like I did not save the training curves, but I did save the results that I got, which we'll see in a minute. But as you can see, we got pretty decent results with a IOU of 83.4. This is after, we'll see, I believe 25 epochs or so, but we'll get back and see. But I just want to flash this screen to you guys and then jump back, okay? Okay, so now let's come back. Now let's go ahead and load the model, okay? Now that we trained, okay? So we have trained this for how long? We have trained this for, actually 100 epochs, okay? Which is okay, not bad. So let's go ahead and load the model, and let's load it. And I put a lot of text here. I have done a tips and tricks video on this topic, because if you try to load this model, right, I saved this. If you try to load it, it will throw you an error saying, hey, you want to load this model, but the file does not exist. Sorry, let me go back. Let me go back, and where did I put that file? Saved _ models, that one. It does make sense to put the right. Okay, now let's go ahead and load this. And it should say unknown loss function, dice loss plus 1 focal loss. That's because this saved model, it doesn't know what loss function we have used. It needs to know what optimizer we used, what loss function we used, and what metrics we are tracking. It doesn't know that. It didn't throw me an error about optimizer, because the optimizer we are using here is basically the standard optimizer. It's from Keras. It's Adam. So it's like, okay, I know the optimizer, but what do you mean by dice loss plus 1 focal loss? I mean, it actually gave a name to this called dice loss plus 1 focal loss, right? Because that's what we are doing. It says, hey, I don't know what that is. Tell me what it is. So that's why I added this next line to show you. You need to tell exactly what custom objects you're using. In this case, we are using a custom object called dice loss plus 1 focal loss, which is basically nothing but our total _ loss. Please don't confuse. This is very important though, if you would like to retrain the model. If you don't want to retrain the model, all you need to do is come here and say compile equals to false. Okay? Then you're all set. It doesn't throw any errors. In fact, if I do that, let's go ahead and load it. It should load it pretty fine. Okay, nothing. So for prediction, that's okay. But if you want to train the model further, obviously you need to load the entire model, including the information about loss functions and other stuff, right? So that's exactly what we are providing here. So that's why when I run this line, now it should throw another error saying, hey, okay, unknown metric function IOU _ score. What does that mean? Because my metric here, wherever I define my metric right there, it knows what accuracy is, but it doesn't know what IOU score is. This is what I need to tell it. So that's exactly what I have done down here, saying IOU _ score is basically from my metrics.iou score and blah, blah, blah. Now when I do this, it should not throw any, it will throw an error if you don't give the right path. Okay, so now let's run this and it should work fine. Let's give it a second. It should work fine. Okay, fine. Now what? Now the whole point of me mentioning this is after 100 epochs, you say, hey, this is not great. Let me load the model again. Now you have loaded this, and now when I run this, let's go ahead and do that. Now I'm training this one more time. It should train. It should not throw any errors. Now it should continue with the previous wherever it left off, and then it should start training. Again, this may sound too basic to some of you again, who have done this many times, but these are areas where I got stuck when I was learning. So I thought, why not talk about it right now? Let's give it a second, but you'll see that it's training, and you see how it started off with an IOU score of 82, 83%. It's still going up. The loss is still being minimized. Okay, and we'll stop this in a second. It's taking about 3 minutes to finish this on my system. Okay, so that's a lot. So let's go ahead and stop it, and let's continue this. Right here. Like I said, if you don't want to train, just load the model by saying compile equals to false, and it should load fine. Okay, it says saved model doesn't exist because I moved it. There you go. Sorry about that. Let's go ahead and load this model one more time. Now let's calculate mean IOU and everything. How do you do that? Well, I'm going to set my batch size to 8. Well, for prediction, I can handle batch size of 8. For training, that became a bit too much. So let's generate 8 images at a time using our image loader, getting data from validation folder and not from the training folder. Okay, that's what we are doing here. And then let's apply the datagen.next to extract the batch of images for and batch of masks. Okay, so that's what we are doing here. So we should see 8 images each, 128, 128, 128, 3 in a second. So where is it? Test image right there. So 8 images of this size, 8 masks of this size, right? So we have 8 images to work on. Next, this part is pretty straightforward. Now we are going to, for the mask, our mask is 1 hot encoded, so let's convert that into an integer encoded, so just argmax, and then I'm going to predict on all 8 of these. So let's get that going because it may take a while. These are 8 volumes that it's trying to predict on. Okay, there you go, that's done. And now if you look at test predict batch, it's 8 images with 4, which is 1 hot encoded, right? So let's convert that into argmax again, to integer encoded. And now let's calculate mean IOU. How do you do that? From Keras, we are going to import mean IOU by providing number of classes as 4, and then providing these two, my test mask and the prediction that we just did. And it's going to give us a mean IOU, which is probably what I have. It's not defined because I did not run that line. Okay, let's do this one more time. So it's giving me 83.4, which is exactly, I think, what I showed you earlier. So that's not bad. 83% with 4 classes on a data set that's this difficult is a good start. Yeah. Again, if you experiment with loss functions and optimizers, and also use the entire training data set for training, and then the validation data set for validation, you may get better IOUs. Remember, we are not using the validation data set. We're not using this validation data at all. In fact, we took the training data and divided that into train and validation, which I should have been a bit prepared, but that's fine. So now let's just predict on few test images. So I'll say, okay, my image number is 200. Go ahead and load the image, load the mask, argmax, prediction, just like we have done right now. So let's do that for image number 200. Go ahead and do the prediction because seeing is believing. Just looking at IOU may not be ideal. So and from this, let's go ahead and look at, I don't know, slice number 55 is somewhere in between, right? Like 128 slices, so about 50s. Hopefully we'll see some data. And let's go ahead and plot it. There you go. That's not bad, huh? This is the original label, and this is what we got. So we can change this to, I don't know, let's just put image number 125. And then do these all the way down and run this to see how well it's doing on this. Image number 125 does not exist. In fact, let's go ahead and in my train, because we split that into train and validation, 125 is probably part of validation. So let's just do, I don't know, image number 96. Yeah, because I see it over there. It should hopefully work. Image number 96. Let's run these. No such filer directly. Oh, sorry. It's exactly the opposite. I'm looking at training. I should look at validation. Okay, now 82. Okay. 82. I hope this works. Okay, fine. And then now let's go ahead and plot something in the middle. Oh, it's pretty good. You see how nicely this is actually segmenting this volume. Now you can be very fancy, try to represent this in 3D plots and all that stuff. That I'll leave that to you. And at this point, you should be comfortable in segmenting these type of data sets. Again, 3D unit is not as scary as you may think. It's just pretty straightforward. Bulk of your time goes into getting the data ready, whether it is geo, the spatial geospatial, whether it is satellite imagery or whether it is brain imagery or microscope imaging, it doesn't matter whether the files come in GeoTIFF format or whether the files come in NII format or some other proprietary format. As long as you have a way of converting that data into NumPy arrays, you have all the power you want in the world to do this type of semantic segmentation. And UNet works like charm. Don't even try other networks. I tried Tiramisu, which is so freaking slow. Tell me if I'm wrong. Okay, tell me if I'm wrong. Give me a network and then challenge me to use that to segment any of these if it's faster. But based on my limited experience of these other networks, I don't even go there anymore. I just use UNet. I'll change the UNet encoder from standard encoder to VGG or something else, but then the structure, the architecture, still UNet is very amazing. Okay, I really hope you loved the last 4 videos on this topic of BraTS dataset segmentation, and please go ahead and like this video if you like it and subscribe to this channel. Thank you very much, guys.